So, in the last lecture we were studying about interesting problem from population growth, and we first introduced the linear model, and we have seen that linear model is not suitable when the population is high, and then we derived the nonlinear model. It is also known as logistic model curve we have not yet plotted, and then the equation which we have seen is dy by dt is equal to a of y minus b of y square with the initial population y t naught is equal to y naught. And we have seen that a solution under we are given provided few exercises. I hope you have already done the exercises by now, and you have produced a solution in the format y of t is equal to a of y naught by b of y naught plus a minus b y naught into e power minus a into t minus t naught. This is valid for t greater than t naught. This is what the solution you have obtained it. And what we have done is that, if you recall the previous lecture, we have seen two equilibrium point. This is the curve t and this is the curve y, and y equal to 0 for this equation, y equal to 0 and y equal to a by b are equilibrium points. Equilibrium points. You will see the exact definition of equilibrium points at a later time, but what the equilibrium points are that y identically 0 is a solution to this system. Similarly, y identically y t equal to a by b, the constants are that are solutions to this system. And from the theory you will eventually understand more and more that when you have two solutions it cannot cross each other. You will see all that. So, whenever you start a t here, y at t equal to 0, it will remain there only. So, you will move along only this line. Similarly, if you mark y equal to a by b, which is an equilibrium solution. So, if you start anything here, it will remain there, and that is all we have explained in the last lecture, and we also asked you to work out the details. Now, if you look at here, this particular term here, as t tends to infinity, this is a minus term here, a is a positive quantity, a is a positive quantity, and this is a positive quantity, and hence as t tends to infinity, this entire term goes to 0. Once it goes to 0, t tends to infinity, this will be. So, you will get this fact, limit t tends to infinity y t is nothing but a by b. Sorry, you see. So, you have an analysis of that one. Now, we want to understand different cases. So, we will come to the next thing. So, we will what you do is some further analysis. We want to do some further analysis quickly. So, whatever I left out, you should go back home and work. So, consider the case 1, first case 1. Case 1. So, 0 less than y naught less than a by b. This the case situation is something like this here. So, you have your a by b curve. So, this is your a by b, and at t naught you are starting the solution here. This is your y naught, and you look at the one of the thing here immediately. What we have seen is that the solution, because this is y equal to a by b, y t equal to a by b is a constant solution, and y equal to 0 is also a constant solution. As t moves, y t has to remain here. This is what the exercises I have given in the last lecture. So, this is also true that 0 less than or equal to y t less than a by b all the time, it will remain, it can never touch these two lines. So, I want to understand how the curve looks like, and we also seen that in the previous slide. If you see, the limit of this one is also is a by b, the limit it approaches there. So, we will go there, we will do that one. So, what will happen, we want to understand. So, look at now this case, interesting case. So, we want to the analysis, we want to understand somehow how the curve, how is the shape of the curve. So, let us try to understand the curve better, you have to understand its derivative, you have to see the sign of its derivative. Dy by dt is equal to ay minus by square. So, this can be written as y, I can take it out, I will take b also outside. So, you will have a by b minus y, you see y at t, but y at t for all time t is less than a by b. So, that shows that this is always positive, y is already positive, therefore, this is positive. That immediately implies this is this case, do not forget this case, it is here somewhere here below a by b. So, this implies y t is an increasing function, y t is an increasing function. That is one observation. So, y t increases. So, you do not have any periodic solution or something like it goes up increasing, but if you want to understand little more about it, what we will do for that, here is an exercise for you. I will be keep on giving exercises. So, one should do that one. Here is an exercise now for you in the same situation. The exercise is that I want to understand, if you want to, so I got some information that y t is an increasing function. So, I have an information that y t is an increasing function, but I want to understand little more about it. If you want to understand more, you have to understand more and more of its derivative. So, you just compute d square y by dt square, you can immediately see that d square y by dt square, you just do computation, it is a plain differentiation computation. You can write here it in a nice way, y into a minus by into a minus 2by, a minus 2by, you see, you can do this. This is a simple computation which a thing. Now, you observe some fact. So, let me think. Sorry. What we have seen that this is a positive number, this is positive. Okay. Now, to determine the sign of d square v by dt square, it depends on the sign of a minus 2by. So, let me write d square y by dt square is equal to y into a minus by into a minus 2by. Here, since this is positive, the sign of this is determined by this will be positive, d square y by dt square will be positive if y is less than a by 2b, and it will be negative if y is greater than a by 2b, you see. So, the sign changes of the d square, dy by dt is always positive, but d square y by dt square changes sign when it reaches a by 2b, you see. A by 2b is the half of the limiting population if you look at it. See, what is a by b? A by b is the limiting population, that is what you have seen. The population cannot grow beyond A by B, limiting population. In fact, it cannot achieve. It like in linear case, where unlike in linear case, where in the linear case it can go to infinity, but in this case it cannot go to infinity. So, A by 2B is half of limiting population, half of limiting population. So, when you start the curve here A by B, you have your A by B and you mark your A by 2B, that is your half of your limiting population, and at t naught, any time t naught, if your population is something is here, till the population reaches the d square y by dt square is greater than 0, what does that indicate? So, up to this area, up to A by 2B, dy by dt is positive. So, if 0 less than y less than A by 2B, in this interval dy by dt is positive and d square y by dt square is also positive. What does that indicate? It actually indicates if both are positive, it is not only the function is increasing, this is basically you can think it as its acceleration. So, you have an accelerated growth. So, the function is increasing in a very accelerated growth, but if you reach if the population reaches half of the population, say A by 2B, and then if the population reaches here up to it never reaches A by B, in this situation you have d by dt is still positive, that means the population is still growing, but then the growth of the rate of growth of the population is it is a decelerated growth. So, this is an accelerated growth, here this case is a decelerated growth, you see. So, you basically get if the population starts from here, it will go very fast growing, the growth is very fast, and then after that still growing, but the growth slowly reduces, the growth rate reduces. So, you get a logistic curve. So, this is called the S-shaped curve, or logistic curve. You see. So, this is a more or less a complete analysis of this problem, when your initial point y, the case 1 where y naught is between 0 and A by B. So, if it starts immediately the population do not grow much, the growth will be decelerated. What will happen if your initial population itself is huge? What is the analysis? And that is an exercise for you. So, here is a final exercise in this problem. Study the case when y naught is greater than A by B. So, this is one more problem to be studied. You can see immediately, you can in fact see all that you can derive. In fact, there is no separated grade, dy by dt is negative and d square y by dt square is also negative. So, that means its a population decreases. So, the moment you have population above the limiting value, then the population decreases and it is a very decelerated decrease. So, it is faster. Again the limit will be still A by B, the limit of the population will still be A by B. So, understand this case. So, the once that you understand this problem completely, you will and sketch the graph. The graph more or less looks like, but you prove it. So, if you start your initial population at time t naught is equal to y naught, then the population will grow like that. So, you get that picture completely. All right. So, there are some comments. As I said in the beginning of this example, the parameters A and B appearing that one is vital coefficients, and that varies, this vital coefficients A and B varies according to which population you are studying. So, there is no definite way of determining A and B, you have to study the population over a long period of time, and you have to do the kind of data analysis in that to determine a suitable A and B. And even this A and B will not remain the same for the same population as the time goes. So, for a certain period of time, even for including the human population, a certain A and B will be good enough, but then you have to reevaluate the A and B after a certain period of time. Secondly, the population model we are given where we have taken into account only the interaction between the species themselves, that is the term you got it by square. But in the natural thing that is not the case, you have to live with other species, even within the single species there will be other issues like national disasters, epidemic, and so many things in a population can come into picture. So, you have to define the model according to the situation, taking into these kind of facts. For example, let me tell you one example which you probably see in our course, or you can not that, as I said initially, it is not possible to explain to you every problem in this course. But let me tell you one important prey predator model. I will just state the equation, I will not give you anything much, but you can see now since the other model is explained neatly, you will it is also called Lotka-Volterra prey predator model. So, in this example you have two species, xt is the species 1, you can say the prey, you can think it is rabbits, okay, so prey, and yt is the population, xt is the population of the rabbits prey, and yt is the population of the predators, foxes if you want. This is just one thing. So, the prey predator model, one interesting, this you can see that in analogy with the previous model, dx by dt you will have Ax, this is the population is growing linearly with respect to the prey. So, if you have a prey, if you do not have anything else, it will think, but then there will be, here I am not taking into account the interaction between the same species, assuming that the rabbits will not kill rabbits or foxes do not kill rabbits, only the foxes will attack rabbits. So, you have a term, the interaction between x and y. So, you will have a term of this form, and the rate of population of the dy by dt, you will have the cxy minus dx square dy square. So, you see this is an interesting, again a non-linear model which not dy square, there is no, this is the growth corresponding to that one, it is because one is eating the other one, you have to understand that one, that is why this is positive side and this is the negative sign, on the other hand this is the negative side. So, this is the again a non-linear system, you will come across with some non-linear system, if not this one, some other non-linear system, and its qualitative analysis will be studied in the coming lectures, we will do that. Okay. So, there are a lot of interesting examples we can do it. Now, I want to go to a next example, as I told you this lecture and next lecture will be examples from the standard nice example. Okay. Initially 2-3 examples I will explain in detail, and then this is a very nice problem, it is actually happened, it is called atomic waste disposal problem, atomic waste disposal problem. As I told you, all these are all very standard problem. Probably to see these examples which I explained here, you can do the book by Brown, which is given in the literature, which is given in the references. So, you can look into the book, that there will be lot more examples. So, it is a very nice problem. It is actually happened in US, where the environmental raised an issue about the disposal of the atomic waste. It is a very powerful atomic waste, radioactive material. What they were doing is that you have the atomic waste, the radioactive waste, put it in drums and sealed it, very strong drums, sealed it, and then they used to dispose it in the sea. So, you will have a deposit sea, the environmentalist, this is the sea level. So, what they were doing it, they were disposing this atomic waste in a place where the depth was around 300 feet. This was the total 300 feet. So, the issue was that when they were disposing this atomic waste at the sea level, it will acquire the velocity due to gravity, and when the thing is that these drums will reach certain speed when the drums reaches at the bottom of the sea level, and it is possible that the impact, the velocity, the impact when the drums reaches the boundary may be so high that the drums can break. So, the environmentalists were protesting against this one, the disposal of the atomic waste problem. So, this problem was given, how to understand this problem, and this we want to see even this, through this problem you can see even how you attack the problem is also important. You may get the solution, you may, as I said earlier, getting the solution itself may not actually solve the problem what you have set out. So, let us calculate. So, calculate, let yt be the position at time t, position at time t. So, you are disposing the thing, and you will the at time t your drums are here. So, okay, this is this length is yt. So, it is all Newton's second law. You will apply Newton's second law, Newton's second law. How do you apply? So, you have the mass of this one, mass m, and then you have the acceleration d square y by dt square equal to the total force. So, it is a question of first computing the total force. How do you compute the total force? What are the forces acting here? What are the forces acting, which you can immediately write, because any simple physics which you have studied. So, you have a gravitational force W, and then you will have a, because it is a water. So, there will be a buoyancy force called, and this buoyancy force will act against the motion. That is what you have to understand. So, you have a buoyancy, this one is coming under gravity down. So, there is a buoyancy force, and then this acquiring the velocity, and you will also have a drag force. So, this is the due to gravity, that is nothing but mg, and this is the buoyancy force, and that you know for water. This is the drag force, but normally the drag increases proportional to the velocity. Okay. So, if I introduce velocity here, so velocity, let me introduce here. If I introduce velocity Vt, that is equal to dy by dt, and the drag force will be proportional to V. So, the d will be something like Cv for some parameter. So, it will be proportional to the velocity. So, you will get that one. So, how do I write this equation? So, if I combine these equations fully in the terms of V, so you will have m into. So, let me write instead of the second order in terms of the velocity, I can write it as the first order equation. So, m into dV by dt is equal to the total force. What is that one? W minus B minus CV. This I will write it in a suitable form. I want to write suitable form, so you can solve it easily. That is why. So, I will write it dV by dt is equal to 1 over m into W minus B minus CV. So, you see that you will have it. So, but I can write this is equal to mg is equal to W, because this form I need it, that is why, that you can see that. You can solve it from here itself, but this good form of writing. So, this is mg W. So, I can write multiply and divide by g, you get mg. So, you get a W, W minus B minus CV. So, this is a. So, let me write it in a form many of you are familiar. I will combine all that there and I can write it in a nice way. dV by dt plus Cg by W into V is equal to G by W minus B, and the velocity you are just dumping it. So, initial velocity is 0 at time t equal to 0, the velocity is equal to 0. So, you see this is a first order equation, first order linear equation. Of course, those who are attending this ODE course for the listening to this ODE course for the first time, they may not know how to solve these things, but most of you I am familiar. Those who have seen some ODE notions, you know how to solve it. Anyway, in our coming lectures you will see how to solve these equations, linear equation. So, let me not spend time how to solve it here, because we are going to explain to you how to get the solution later. So, let me, what I am going to do is that I am just plainly writing my solution. So, the solution will be Vt is equal to, I can immediately write, this is also a non-homogeneous equation, there is a non-homogeneous term. Okay. So, it is a first order linear non-homogeneous equation. So, this term in this form gives you the linearity, this gives you non-linear, and we will explain in detail how to solve it when we study the first order, second order, all that equations. But let me write down the solution very nicely. The solution is W minus B by C 1 minus e power minus Cg by W t. This is the solution. So, what is our aim? As far as our problem is concerned, the aim is to see that the velocity does not reach where the breaking level, and that was calculated, that is calculated by the people. If the velocity Vt is approximately something like 40 feet per second, these are computation done by the people, environmentalists. If the drum, you drop the drum and reaches the bottom, by the time it reaches the bottom, if the velocity reaches crosses 40, then there is a chance that these drums will break. So, we want to see that by the time it reaches, the velocity will keep on increasing, whether that is why the analysis is now required. Whether if your solution never reaches 40, then there is no problem, it is not going to reach and 40 and then head. But then now you compute this, as an immediate analysis you can do, limit t tends to infinity, Vt is equal to this, as t tends to infinity, this term goes to 0, right. So, let me mark it with a color. This term goes to 0 as t tends to infinity. So, immediately you see that the limit goes to w minus b by c, and these are all known quantities. W, b are all, and c, these are all known quantities, because w is mg, b is the buoyancy which is has a value, c has the proportionality to the drag force to the velocity, and these are all computed, but this is approximately happened to be 700, you see. So, the velocity indeed will cross 40 as t tends to infinity, but there is nothing to completely ignore the problem here. It only says that the velocity can cross 40 at certain time, but that does not mean the velocity will reach 40 by the time, suppose it hits much earlier time the ground. If it reaches and hits the ground which is only 300 feet, at that time it may not reach 40, then you are fine. But from here, from this computation, we are unable to judge at the time it reaches, because we do not know the time, what time it will hit, because we have calculated the velocity in terms of the time, we have not calculated the velocity in terms of the distance. That is where a different approach. So, this approach, even though it looks like your problem is solved completely, we are unable to predict what the actual problem was, actual interest was about the problem. So, we have to view this problem, we have to analyze this problem in a slightly different way, and that is what we are going to do it now, another approach. So, this is again to indicate solving just differential equations may not be the entire aim, and in fact solving may not give you what you want, and quite often it may not be necessary to solve get the solution explicitly. The aim of the problem will be quite different, which you have to learn it. So, the idea is that you have this problem and you are dumping it, you want, so far you calculated the velocity as a function. So, the velocity is your dependent variable and time was your independent variable. Now, what we are going to see is that you are viewing this distance, y is the distance, indeed the distance earlier also, but you have seen the difference was that you viewed the distance y as a function of time. Now, I am trying to view y as a independent variable, and then you calculate the velocity. So, it is going. So, you are calculating the velocity v of y, velocity at distance y. So, the time is not coming into picture in this formulation now. So, but we need that one. So, v is the velocity at a distance y. So, we are computing in the downward direction, which you understand, I hope, at a distance y, you see. So, that is why. So, y is your independent variable now, v of y is the velocity as a function of the distance is the dependent variable. Of course, at time t you already have. So, y equal to t is the distance at time t that you still exists. So, if you if you derive my relations, v is the velocity at time t, at time t your distance is yt. So, v of t is nothing but v of yt. So, this relation you already have it, you see. So, at time t you are at a distance yt, and then the velocity at that time function vt. So, you compute these things. So, it is a question of computing dv by dt is equal to nothing but you have to compute dv with respect to y and into dy by dt. But dy by dt is the velocity, that is nothing but v. So, this is nothing but v into dv by dy, you see. Now, substitute. So, you computed dv by dt in this equation, you substitute that equation, substituting in the earlier equation, you get it, substituting, what do you get it, v into dv by dy is equal to let me just write the equation, the same equation I want to do, Cg by W v equal to G by W, W minus B. You can derive to this form. So, if you do not get it, you can get this equation. These are all simple computations which you should do it. You substitute or you do the computation, as I said, do the computation. Okay. And I write this equation in a slightly, here there is a problem. The problem is something serious now, because this, so earlier in V the equation you got was a linear equation, linear homogeneous first order equation, but look at this term, this is a non-linear term. So, the moment non-linear equation, the moment we have changed the way you view it, that is why the other model derived first, thinking that that will give you the answer, but the required answer we did not get it. So, when we change the model and view this V as a function of the distance, we have a non-linear model, and we have to analyze this model nicely. So, you will I will give you some more exercise probably. Okay. So, I will write this exercise. This is a simple computation, you do not have to worry, but you should get familiarity with the computation. Write the equation as, I want to form, even though it is a non-linear equation, I want to write it in the solvable form. Write the equation as, this is easy to do it, equation as, let me write it, V by W minus B minus CV into dV by dy, which is not difficult to write, is equal to G by W. See, non-linear equation solving is, there are no general methods at all. So, you have this equation. Now, this is an equation in V, dV, dy you can take it out the other side, and of course, the velocity initially is an initial value problem. So, you have a V0 is equal to solve. This equation can be integrated, solve it. This is a solve it. This is a standard integration problem. It may look complicated, does not matter. What you can add is that you can make a numerator similar to this one. First you multiply something, you can take C outside and do all kinds of things. If you take C outside, you get W minus B by C, and V is there, you add and subtract something. So, you can decompose it in a partial fraction or whatever form it is, which you can solve it and solve it to get. If you do not get it, at least after a few lectures in differential equations, after studying the basics of differential equation, you should be able to solve it. But you need not have to know any differential equation to solve this one. So, this is an integral problem. So, you have to just integrate it, which you can do it, because dy, this is in a at least way, even though it is non-linear, it is a, this is a constant. So, G and GW, this is a constant, so you do not have to worry about it. So, dy you can take it, it is a separable form and integrate this function. So, basically want to integrate this function, you are in the, you have to integrate this function and substitute this thing to get it. So, let me write down my solution in a, to get a solution in an implicit form, Gy by W, this is an implicit form, equal to minus V by C minus W minus B by C square. Anyway, do the computation. If I have not make any error, I am not sure, there may be some minor error of sign or something, but it is nice to correct the error of the lecturers, and that is the best way to learn, in fact. So, you see is the thing. So, that is the final form of the solution. So, earlier you have a better form, you have a better thing, but this is a more complicated form of solution, more complicated solution, but and you cannot separate it, even you cannot represent. So, you see this is an implicit equation, there is no easy way of representing V in terms of Y. But what is interesting they have done is that is the final tail, tail to the tail, okay, tail to the tail if you want. Okay, both the tails are different. Okay. What they have done some numerical computation, and what is your aim? Do not forget the aim. The aim was to compute V, the velocity when it reaches a distance 300, right. That was the initial aim. You want to know what is the velocity when it reaches here, and they did some computation. It happened to be approximately 45 greater than 40. You see, so you wanted that to be less than 40, but unfortunately it happened to be 45, and then eventual result was that they had to stop dumping it. So, it was a protest from the environmentalist, and they have to see how the mathematical simple analysis one has to deal with to solve problems. Okay. With this example, I will now go to, I will not give you the details here. I want to give you 2 more examples. I will not be able to complete the analysis, but these 2 more examples are extremely fundamental in 2 of the fundamental areas of engineering. One from mechanical engineering, and another from electrical. And these people, the mechanical engineers, electrical engineers regularly use these examples. In fact, any automobile, any things you do it, any construction, even civil or whatever mechanical construction thing, these examples will work. So, I will today I will try to give these 2 examples how they produce. The interesting aspects of these examples are that both leads to the same differential equation. If you recall my first lecture, the aim was that even though the differential equations may be coming as modeling of different physical phenomena, the mathematicians always want to study in a very general perspective. It may have common features. This is one of the interesting very simple examples which most of you are familiar. Those who are again taken a course on ODE will be familiar. It gives you a non-homogeneous second order linear all simple equation with constant coefficient which you can solve it, you see, V both leads to. So, we will derive it the equation, we will show you that equations, how the equations are coming, and maybe in the next lecture we will do an analysis of that, and this is the complete thing. After that we will explain few more problems in the next lecture, but we will not you will see some of the examples as we proceed the course thing. The thing is that it is a mechanical vibration problem. So, I will do this one, mechanical vibration problem. This is a model which you are on a regular use, which all of you see when you drive a motorcycle, when you drive and hit a hump, what is it doing? Especially the concept of shock absorber, the basic thing is in the mechanical vibration model. So, it is also called spring mass dashboard system, spring mass dashboard system. You see, okay, that. So, it is as I said, it is use absorbers in automobiles. It is also barrel heavy guns. When you fire a gun, you know that it's also comes back to hit you, and you have to understand that in a better way how to avoid that one. And the main thing is the shock absorber. Okay. So, what is basically a spring mass system? So, you have a spring, natural spring attached with a mass here. So, you have a mass M and you have a spring. You have a spring mass. This is called the spring mass. Spring mass. You see. How does it work? Suppose you pull, suppose its length is L right now. This is L basically. You pull it or push it, whatever it is, a length, pull or push a length of delta L. Then the spring has the thing of the restoring force, that is what the spring will do. Spring will try to restore, when you will pull it, spring will do that one, and this delta thing, it will exert a force proportional to delta L, and that is we call it K into delta L, and that is how the spring constant, this K is called the, depends on the how strong your spring is, this is called the spring constant. Okay. So, it is an important parameter. So, K positive spring constant. So, you will have vibrations by Newton's second law or first law. You have to say that when you have a spring and if there are no external forces, nothing else, when you start vibrating, it should start vibrating without stopping. We want to see all that phenomena thing. Now, how do you create a spring mass thing? When you are getting a shock, when you are riding a vehicle and hitting a hump and you get a shock, you do not want the vehicle will feel a shock, you want to reduce that shock on your body, you do not want to get it. That is what shock absorbers will do it. You want to remove that shock, you want to decay the vibrations created by unforeseen circumstances by heating or something like. Of course, if it too much, your shock absorber and other things will not take care of it, but you want to see that one, you want to see that. So, what you do is that you put this spring mass system in oil, whatever it is, you put it in oil, whatever it is. So, you want to understand. So, as soon as you put the spring mass system, put it in oil, the oil will have its own effect on that spring mass system. When there is nothing, by Newton's law, it should start vibrating. When you pull it, it will keep on oscillating, and that is what it may suddenly create, but when you put it there, you want to do that one. So, you again want to the Newton's second law of motion. What do you get it? You will have again, if the mass is m, you will have d square y by dt square, and what is yt for you here? Yt is the distance from the measured distance at time t, distance at time t, measured in the downward direction, measured at distance at time t. So, you have the total force, that is what you have to understand, what are the total forces will come. Okay, let me reserve this one, total force. So, you want to understand what are the forces. There will be a force due to gravity, and what are the other forces? There will be a restoring force. The spring has an effect, I told you. The moment you pull it, this will have a restoring. The spring will try to restore it to its original position, and that will act against the motion. For example, if you pull it, it will go to the position. If you will push it up, it will come back. So, the restoring force will have an apply against this is the gravity, it is coming down, and then what are the other forces available there? You will have a drag force, and that also act against it, and then some external disturbances, that is what more interest. So, you will have some external force. Okay. So, this is due to gravity. So, that is nothing but your mg, and then you have the restoring force. How do you compute that one force? So, you have your restoring force, you have to write it. Suppose it is a yt, and if you pull a distance of delta L, and so the restoring, so y is the distance at time t, and you pull it a distance of delta L, the restoring force will be yt plus delta L. So, yt at time you pull it, that is a restoring force, and drag force, as I tell you, is normally proportional to the velocity. So, you will have c into dy by dt, that is the velocity. Okay. So, these are the terms you have to apply, but now we are analyzing the situation at equilibrium. At equilibrium, what will happen? So, when it is an equilibrium, the one created due to this pulling should be cancelled with your gravity force. So, you are exactly you will have it mg, that is nothing but your W will be equal to the k into delta L. So, that is what will happen. So, you have to write down the restoring force. I should not put sign here. So, basically you will have k into delta L. So, final equation, if you rewrite all these equations, comparing here, you put it here everything, what you will happen is that after cancellation you will have an equation of the form, you rewrite, derive, finally do a bit of computation, finally m into d square y by dt square plus what you will have is that c into dy by dt plus ky. All these terms will come, you see c into dy by dt will come, and I have taken the sign. So, it will come here with a minus sign, you will have a sign here that will come here, and the other terms will get cancelled, only one term is equal to f of t. So, you have you see this is a, so you have to understand these terminologies. M is mass, this is called the damping. Basically you are putting a damping, you have to understand why mechanical system you need damping. Okay. If you do not have mechanical damping, it is exactly due to that you are putting it in the oil. Okay. You are putting this system in oil and creating a damping on the system. So, whenever you create any mechanical system, you have to give enough damping, otherwise it will create oscillation. This is about the spring constant, you see it is a spring constant. Okay. So, all these terms m, c, k are positive. This of course, it is an external force which you do not know. So, you can have an external force. So, you have to analyze this system, you know how to solve. Suppose f t equal to 0, you know this is a second order, as I said second order, earlier equations were first order, now you have a second order, easier thing, it is in a linear and with constant coefficients. So, you have all simple form with constant coefficient, and we know how to solve it. We will do this solving later, but I will write down the solution and I want to interpret. Now, from these last two examples you have understood, just writing the solutions are not enough, you have to write the solutions and you have to interpret the solution, what are the things happening in a mechanical system. And so, when you design a mechanical system, you have to take into account how much damping you have to put into the system, what is the minimum thing required, so that you do not have the vibrations of your mechanical system. There are disasters due to the lack of damping. Okay. So, we will do that in the next lecture, but in the few minutes I am having, I just want you to show one more example leading to the same example, electrical circuit. Electrical circuit, simple electrical circuit. I want to do this. This is an RLC circuit, simple RLC. So, you have some EMF coming from here, electromotive force coming connected to an resistor, and you have a inductance and you have the capacitance. So, you have plus, I hope the minus sign, if you want you can put a key. This is a simple RLC circuit. So, you have your resistance here and you have the corresponding inductance here and you have your capacitance, and what are the things you have it? You want to understand the current IT at time t, and you have the charge. Suppose Qt is the charge at the capacitor charge. How do you model this one? This is a closed circuit, simple closed circuit. So, you apply Kirchhoff law. I told you the correct physical laws you have to apply. So, you have the Kirchhoff law. So, the Kirchhoff law it exactly tells you that E t is the total voltage drops, total voltage drops. You have to understand the voltage drops across all these things, and then you are through. You write down that one, and that simply. So, across L, what is the voltage drop? L into di by dt. That you know it. This is comes from how they design. That if you know little bit of electrical circuits and the equipment, you can see that this is the kind of voltage drop. That is nothing but you have also a relation here. IT is I is nothing but dq by dt. Okay, so you have that also, this relation. So these are standard things which when you study the basics of this one. So this is nothing but L into d square q by dt square, and across R you have this that you know it, nothing but R into I, right, the voltage drop. This Ri, that is nothing but equal to R into dq by dt, and across C is nothing but 1 by C is nothing but q by C, and you have to write an integral form if you want to write the I. So, it will be q by C. So, if you add these three, your equation is, you see, equation is L into d square q by dt square d by dt square plus R into dq by dt plus q by C, 1 by C q is equal to E t. You see, it is exactly the similar equation as in mechanicals, absolutely no different, only the quantities are different, the interpretations are different. So, you have a similar equation. So, quite often the same equation, the previous equation is written in terms of current. What do you want? If you want to write it as a second order equation in terms of the current, you differentiate once more. If you differentiate once more, what you will get is that I into, so you can write in this format also, d square I by dt square plus R into di by dt. So, you can write this equation in this form plus 1 by C I, but you have to differentiate once more. So, you will have basically E prime of t, the derivative of this thing. So, you can see a comparison, it is an analogy, it is not really a comparison, but you can have analogy, because in the mechanical system I am going to do a detailed analysis. A similar things can be done for the electrical system also. The interesting thing is that in the mechanical system you can see that, so both places, that just like you there you use damping, in electrical circuits you use resistance. So, and unwanted vibrations, what you have seen, you are there, you are putting the thing to remove the vibrations, and so you want to have a stable system, but the use of that in electrical circuit, we want to create that amplifications. So, the same phenomena there you have vibrations and removing through damping, which you will see is used. You do not want unwanted vibrations in the mechanical system. So, the bridges etc. This exactly what happened to the Tacoma bridge collapse, which we will explain later. On the electrical systems, the same things are used, the frequency modulator is used to amplify, to correctly, this is exactly the principle used to match the frequency and to tune your radios and other television sets. So, how do you get all the signals are coming into your television system, and you are want to get that. We will explain this one, we will do the analysis on these systems more, and in the next lecture, and we will continue it the next one. Thank you.